Hi, welcome to Elephant in the Room. These are short adventures in geography designed to make you think. The idea is, wherever you see this red stamp, I want you to stop and think about what we're doing. Alright, this time we're going to take a little look at the global water cycle, a fundamental part of how Earth's geography works. Because understanding geography, like a lot of things, is not just about knowing a load of details, the oxbow lakes and the types of erosion and all that stuff. It's also about understanding how these things fit together. And really, that's what makes all these details useful and interesting and worth finding out about in the first place. So, the Earth's surface is all about water. All that ocean and cloud and ice absorbs and reflects and distributes and dissipates the deluge of energy arriving from the sun. Water is where all the short-term, intense surface chemistry, the regulator of just about everything on the planet, takes place. It's the portal to Earth's geology. Water is how the physical material of landscapes is continually shifting about, and why the Earth lacks the pockmarked surface of the moon next door. Water is life and death to all the complicated ecosystems and the living things living in them, which are not much more than fleeting packets of salty water held in thin carbon membranes. The Earth's surface is like a smorgasbord of what's possible with water. The vast majority of the water on Earth is, of course, in oceans, which form a continuous skin over the Earth's surface, dragged about by the gravity of the moon and the sun, whipped up by winds and flowing in response to changes in density as its temperature changes from the equator to the poles. At our sort of scale, oceans are enormous, and while I can tell you from bitter personal experience that they're horrible, inhospitable places for creatures like us, they're actually only a few miles deep, and the surface, where the light gets in, is so full of microscopic life that it's practically soup. This thin water skin has been there virtually as long as the planet has existed, and the frothy continents poking out to form bits of land have gradually built up in it over a few billion years of sedimentation and plate tectonics and volcanic processes. Over just the last few million years, in a sudden deviation from the Earth's usual pattern, large quantities of ice have accumulated at the poles, periodically expanding and contracting in response to variations in the Earth's orbit around the sun, sometimes getting almost as deep as the oceans. Under the enormous weight of all this ice, the continental crust gets pushed down and ice is squeezed out from the margins like toothpaste, carving out valleys and scarring the surface and depositing massive excavations in front of it like gigantic bulldozers. This ice, like clouds and deserts, has high albedo, which means it reflects light back out into space and helps to keep the planet cool. When it retreats, the newly exposed darker crust slowly recoils back up and can start warming up in the sun again. And in between the ice and the oceans, the ground is like a saturated sponge, holding water for many tens of thousands of years in aquifers. Sometimes these break the surface to form lakes and to give birth to rivers which snake their way across the surface on much shorter timescales. They wiggle back towards the sea, eroding their channels and depositing their floodplains, joining up to form tree-shaped drainage catchments which jostle about and gradually decrease their slopes as they go. In the end, they meet the sea, pulsing up and down, daily with the tides, mixing the salt and fresh water in muddy estuaries and in muddy deltas. And across all this, the carpet of life has slowly crept out of the oceans to extend its reach over the land over the last few 100 million years or so. Much of this land-based life is in the form of more or less well-organized soils, holding some water too, and only the fuzzy photosynthetic tips poke out above the ground. At the scale of the water cycle, though, this living stuff accounts for barely any of the water on Earth, and the part of the world we animals occupy, essentially the servants of those plants, is just on the very outer edges of that. At the scale of just days, water cycles through the atmosphere, another watery skin just a few miles thick, but much more diffuse. Water evaporates from the surface of the ocean, rises into the atmosphere where it cools and condenses to form highly reflective clouds a mile or two above the surface. Pushed about by winds as the Earth rotates, most of the water falls back into the sea again as rain, but some of it makes it as far as land, where it arrives in sporadic waves, breaking especially on higher ground, feeding rivers and life and recharging aquifers. Some places get more water than they can handle, and it spills out over the land as floods, suddenly reconfiguring the channels and drainage patterns till the next time there's too much. Other places get hardly any at all, leaving the bones of the planet exposed to the winds, like bits of Mars on Earth. Just a tiny, tiny fraction of the water in the atmosphere makes it all the way to the poles, where it falls as snow, and if it stays cold enough there for long enough, it doesn't melt again until it's reached the end of a glacier, or it's carved off as an iceberg, which floats away in search of melty adventure. So that's the water cycle. It's roughly in balance. All the water moving from the oceans and onto the land via the atmosphere makes it back to the sea again via rivers. So now we have a bit of an overview. Let's do a few calculations about some of the interesting bits in it. Although plants, these fuzzy photosynthetic tips of life on the surface of the land, only contain 0.001 zetagrams of the Earth's water, they're engines of something called Vapo Transpiration. They suck up water from the soil, draw it through their bodies, and liberate it into the atmosphere as water vapor through their stomata, tiny pores on their leaves that open and close in response to conditions. Globally, this upward water pumping is estimated to put about 0.07 zetagrams of water per year back into the atmosphere. That's a lot. It means that on average, the water in plants, maybe 90% or more of their total weight, is passing through them about 70 times per year. They're completely replacing their water content about once every 5 days. They're like leaky balloons kept inflated by this evapotranspiration flux, more like slow-motion fountains than solid things. No wonder they start wilting after just a few days without water. And it doesn't stop there. The global average rainfall onto land surfaces is about 0.11 zetagrams of water, and 0.07 zetagrams of that is water from this transpiration. So on average, something like 2/3 of the rain falling on the land is water that's already passed through plants. Plants are recycling their water through the atmosphere big time. They're making the rain, keeping themselves wet. Think about that the next time you're caught in the rain. You're standing in what's only just slightly diluted plant waste falling from the sky. At the other end of the scale, we hear quite a lot about sea level rise in relation to global warming at the moment, and this is because there's a lot of water stored at the poles as ice, and we're seeing it melting at an alarming rate. There's about 24 zetograms of water stored as ice, and when it melts, it adds to the water in the oceans. The average depth of the oceans is just 3,700 meters or so. So if all the ice melted, that would increase sea level by something like 66 meters. Thanks to all the movement of sediment by rivers, coastal land has very low average slopes, about 1.8 degrees, and often a lot less than that. So that 66 meter potential sea level rise means the sea moving a couple of kilometers onto the land along the entire coastlines of the planet. In nearly flat areas where humans like to live and grow their crops, it's much more than that. This is already becoming a real problem for us. For example, most of our cities, for very good reasons at the time, grew up right next to the water. So all this ice is not a constant thing either. When you look at climate cycles in ice cores and so on, we're in an interglacial period when ice is at its minimum, and we're close to the peak temperatures seen over the last few million years while these glacial cycles have been going on. We're due for another colder glacial period soon, when ice builds back up again. In fact, most of the time humans have been around on the Earth has been spent in two very long, slowly intensifying glacial periods, and modern humans only really took off when the climate suddenly warmed just 12,000 years ago. The sea level during these glacial periods is thought to have been about 120 meters lower than today, exposing great big bits of coastal land extending outwards towards the continental margins. This was presumably an important part of early human habitat, and now it's inaccessible, hidden under lots and lots of water. Who knows what secrets are down there? Given the sea level change, the ice sheets during these glacial periods would have locked up about 70 zetograms of water, and we can tell from geological surveys that these much bigger ice sheets spread out far from where they are today, covering many of the areas we now call home, almost all of Europe and North America. So our early history is not discernible in these places either. It's a wonder we know anything about ourselves at all. But it looks like this next glacial period, due to start sometime in the next few tens of thousands of years, may not happen at all now. Clever calculations by scientists suggest that humans have pushed so much carbon into the atmosphere so quickly that the next natural switch to glacial conditions is unlikely to be triggered now. That's a measure, another one like the rate of extinction, of just how profound human impacts on the planet have become. Whatever the planet was up to with its natural glacial cycles looks to have been interrupted even before humans have managed to figure out what the consequences of that might be. Maybe this is humanity's role on spaceship Earth. Who knows? One thing's for sure though, we don't. And this, in a way, brings us back to the point of this video, that just collecting lots and lots of disconnected details is not really enough. It's really about how all these details fit together. It's about getting a good enough overview of how a whole system works, that we can see what's going on around us and perhaps start making better decisions. So, your challenge this time, should you choose to accept it, is to use the numbers we've got for the water cycle and your own research, if you like, to estimate the average residence time of water in ice at the poles. That's how long the water arriving at the poles as snow spends as ice. And then I want you to compare your estimate to how long glacial periods tend to last. Is the ice at the poles a bit like the water in plants we looked at, rapidly replaced over and over and over again? Or is it more like a giant accumulating pile of frozen water, constantly building up until something clicks and it all suddenly melts? See what you think. Thanks for listening, and see you next time.